Welcome back to the Save It for Parts channel. In some prior videos, I've been working on turning these small camping or RV satellite dishes into radio telescopes, live low Earth orbit satellite trackers, and other things that they were never meant to do. These are originally television dishes to put on top of your camper, on top of your trailer. I like to take them apart, swap out the parts. In this one, which we showed in a prior video, I have an L-band helical antenna, and this thing works great for picking up L-band microwave NOAA weather satellites, Russian meteor satellites, European METOP satellites. It's all around a really nice automatic tracking system for low Earth orbit satellites in general. This video is sponsored by PCBWay, who offers an array of rapid prototyping services that can be really helpful for a project like this. They are not only a printed circuit board manufacturer, which you might expect from the name, they also offer laser cutting and 3D printing. Now, in the last video, I 3D printed this helical antenna and helical feed in the center. And for this video, I am also 3D printing an S-band feed. Now, this is a challenging print for me. I have a lot of trouble with this, and it takes me multiple attempts to get this to come out correctly on my 3D printer. So if I cannot get this to print, I was actually considering going to PCBWay, sending them the file, and having them prototype the device. Now, I did eventually get mine to work, but it was very frustrating. It wasted a lot of PLA, and it would have been a lot easier to have PCBWay do this for me. If you don't have a 3D printer at all, and you want to do projects like this using 3D printed parts for custom antenna designs, well, PCBWay is a great solution. You can upload your STL file, upload your designs to them. They will make the part for you, ship it out to you, and it's very affordable. And of course, they have lots of other great services as well. If you do want a custom printed circuit board designed, maybe you want to make your own control brain for something like this azimuth elevation rotor. Maybe you even want to make your own realistic satellite model or CubeSat experimentation platform. Well, PCBWay can help you turn that printed circuit board design into an actual physical product. I'll throw some links to PCBWay down in the description below. They are not just a random sponsor, they are actually somebody that I enjoy working with. They are very friendly people, very helpful, and I really recommend them. I even met some of the PCBWay folks out at OpenSauce in June of 2024, and they're really nice folks. They're really easy to work with. Big thank you to PCBWay for sponsoring this video and helping me make this project possible. Now, I would like to take this a step further and go for a larger antenna, and that's going to involve this Trav'ler model dish, which is also made by Winegard. This is a slightly bigger one, also designed to go on the roof of an RV or a trailer. It's a little hard to see here and all the junk in my garage, so we're going to pull this out and take a look at it. So I've looked at this thing briefly in another video. I got this for free. It was missing some parts, but it does mostly work. I did have to hack in a power supply, and I had to hack some cables together to get the indoor unit, this little control box here, to talk to the outdoor unit. The brains of the operation are actually inside the outdoor unit. They're inside this turret, and that is controlled in much the same way as the other little Winegard dishes that I've been using through an RS-485 serial port. That's this weird little interface here. It looks like an antique phone cord jack, but it takes 6 pins instead of the usual 4. Side note for anyone else having to hack this cable, or for future Gabe when I inevitably break this again, the wiring order here from top to bottom, left to right, is green, yellow, orange, and then on the bottom it's red, brown, black. And this power supply is 48 volts DC. I'm using 52 volts because that's what I have and it's close enough. Now, all these Winegards have a really annoying initial setup system where they power on. In this case, it unfolds itself and then it spends like 15 minutes looking for a satellite. Now, I don't want to wait for the full Winegard dance, so I'm going to try to log into the brain on this thing and tell it to just kill that operation. I'm going to need this RS-485 to RS-232 to serial cable. I've used this in the prior videos with Winegard equipment. They're all pretty much the same. I'll put a link down below to how to make this if you're interested. Alright, I think we have killed both the search and sweep tasks, and the dish has stopped moving, so that's a good sign. Now we can actually do something interesting with it instead of wasting our time on television. Now, the firmware on this is very similar to the other units I've looked at, but not quite the same. So if I want to use the same code that I did for the Winegard carryout, I'm probably going to have to modify some of my commands that get passed over that serial connection. Now, we're still connecting with the same port and baud rate, but with the carryout, we had to go into the target submenu, and with the Trav'ler dish here, It looks like we've got a PA menu, or point angle, instead of target. This might not quite be what I want. We're in some kind of subroutine that keeps crashing. This lets me select a motor and tell it a pointing angle. So this is close to what my other code did, but not quite. And I'm not quite sure what it's trying to do here with SLK. I'm not quite sure what that means. This looks a little more promising. These Winegards tend to have 3 or 4 different submenus that all do essentially the same thing. So there's usually a motor menu, a pointing menu, a motor board menu. This one looks like the motor debugger, and it looks like we can do all kinds of stuff here. We can send a particular motor to a position. Yeah, here's another duplicate motor submenu, and it looks like we can do the same thing here. We can send a given motor to a given angle. I'll just verify that by listing the available motors, and yes, we have 0 is azimuth, 1 is elevation, 2 is skew. All right, I was hoping I could just fire up my previous Python code from the carryout dish, run it on the Trav'ler, and have it track some satellites, but we can't do that just yet. We have to modify the code to use the commands available in the Trav'ler's firmware, which are a little bit different from the carryout's firmware. There's a carryout G2 and G3, which are very similar to the original carryout that I use, and I do have a couple of those dishes, although I haven't done as much with them. If you want to see some of the code for those dishes, I have some on GitHub, and then a fellow who's on my Discord going by C. Davidson has also done some code for the carryout G2, which looks a little bit better than mine and does some interesting things. So I'll throw links to all that down in the description as well. Anyway, long story short, I'm going to have to go back inside, sit down at the computer, and rewrite my Python code. I've been fighting this thing for a little while. It keeps locking up and giving me a command rejected. I realize there's a typo in the help menu. So in the motor submenu, it tells me I can do G, azimuth, skew, elevation. Well, that kept giving me command rejected. It's actually as elevation skew is the correct command format. So somebody just mistyped this when they did the help menu. All right, I've got it sending 3 values over here, but the antenna does not like it. This dish is pickier about what commands it gets and how fast. If you send another command while it's trying to execute the first command, it doesn't like that and it shuts down. The other Winegard carryout didn't care about that. The downside of working on a project like this in the garage is sometimes there's a car in here. Personally, I think the garage should be for boats and satellite dishes, but my partner likes to park her car in it for some reason. I just don't understand. Yeah, I've gotten myself into a bunch of hang conditions here. This is really frustrating. This thing is giving me weird serial returns. The computer doesn't always know how to interpret those, so if I don't catch it right as it comes through the console, then it just gets stuck in a loop. Probably none of that made sense to anybody except me because I'm the one writing the terrible code, but it is turning out to be much harder to interface with this one than with the little Winegard dishes. Now, it will only run one motor at a time. It won't run azimuth and elevation. Not quite sure how that's going to work for fine detailed tracking when something is directly overhead. I'm also a little scared to do anything too crazy in the firmware or change any settings because I'm talking to another fellow who's working with one of these, and he has completely killed the connection between his outdoor unit and indoor unit just by turning off the GPS. This should be moving much quicker and not having these long pauses in between motions. I'm still not quite sure what's up with that. I'm also not getting my position feedback working. I was trying to send the current azimuth and elevation. That has not worked reliably. I'm mainly explaining this to myself because I'm not going to remember what's going on here. So now I have too much precision. I'm calling for motions that are actually smaller than the gear slop allows. So it's trying to move, but it's taking a second to catch up because there's a little bit of play in the gearing. Now that I have the mechanical part of this antenna somewhat functional, I'm going to start working on the radio reception part of it. So the main part of this antenna is going to be a helical feed. This is a 3D printed scaffolding that I got from Derek SGC on Thingiverse. Derek has a great YouTube channel as well with lots of satellite and radio stuff, and he's got some really interesting designs for 3D printing. So if you want to make one of these for yourself, I will throw the link down below. And then, as I probably said earlier in the video, if you don't have access to a 3D printer, or if you have trouble printing a complex shape like this the way I do, you can use PCBWay's 3D printing services to send off the file and they will mail you the completed product. Anyway, I've already started winding some scrap copper wire into this. So this is a left-hand circularly polarized feed because we are using a dish, so the signal bounces off the dish and into the feed. If you saw my helicone, that is a right-hand circular polarization because the actual signal coming from the satellite is right-handed, but again, the dish reflects it. So this will be left-hand, and this is a, I believe, 5.5 turns. I do have to do some cleanup. I have to cut off this bottom piece and solder it onto a ground plane. And the ground plane is just this piece of thin sheet metal with a SMA, a very small SMA connector, bulkhead connector or panel connector here, poked through the middle, and then we will solder that spiral piece of copper wire onto the center piece. So in addition to the antenna feed here, I also need an amplifier and down converter unit. Normally I would use something from NOAA like their Sawbird series, but unfortunately they don't make one for S-band. So instead I've got this MMDS, which stands for something. Apparently this was used for some kind of gimmicky wireless cable from the 80s. I grew up in Alaska where we were always at least 20 years behind the times, so I never actually saw one of these when I was a kid, but yeah, this is one I used in a prior video, and after I did that video, people said that I put the wrong connector on here. Apparently, a VHF or CB radio style antenna connector is not good at microwave frequencies. I don't understand the math of it. Apparently there's just something about that shape that's not quite as good as this shape for higher frequencies. So we're gonna put a in-mount connector on there, which is commonly used for S-band. Hopefully I haven't destroyed this. This stupid in-mount connector, it did not quite fit, so I had to do some dremeling. I had to make it fit in there. And then there's this just whisker-thin, tiny wire in there. I am not a tiny wires guy. I am a big, kludgy hands guy. Now for alignment on my feed, I think what I want is the first turn to be basically at the focal point here where the white part of the L&B is. Now, I'm gonna take this L&B off, and I might repurpose this bracket here to stick my feed onto. I just have to lean it back a little bit so it's in the right orientation. One tricky thing about this particular dish, it is designed to stow or face plant onto the roof of an RV. So I don't want to do that with this little helix attached because this is not very sturdy. All of this extra stuff here, this bracket and whatnot, are part of that stow mechanism. The front of this actually folds up on a spring. So I'm going to try to not do that. I'm going to try to disable that in the software so we don't face plant onto the feed. Okay, I think that is mostly correct, or at least I hope so. S-band takes a little more precision than L-band. You can see L-band over here. That is just kind of smashed in there with a cookie can lid on top, so that is not super precise. This one I've tried to do a little bit better job with it. All right, I think it's time to give this a real-world test. It is a really inconvenient time as usual. It's kind of late at night here, but we have an S-band satellite coming overhead. May or may not be actually working, so I don't know if we're actually going to get anything from it, but we're going to give it a try anyway, see if we can at least track it, verify that the code is working, verify that the dish is working, and if we're lucky, we'll get some kind of a signal. All right, it does seem to be tracking, and we do seem to be getting something on the computer, although it might just be a carrier frequency. I don't know if we're actually getting any data from this. All right, yeah, SatDump didn't even try to decode that, so... All right, it's another day. It's actually Christmas Day, and in between baking and chasing the cats off of my baking, I'm trying another satellite pass. So we're getting set up for good old NOAA 18, which should be coming over very shortly, almost a directly overhead pass. So this is pretty much ideal conditions to test this out. And there's still plenty of room for failure with this system, so we're still ironing out the bugs, and we're gonna see if we can get it to work reliably. Well, the tracking part seems to be working. It's definitely trying to track a directly overhead pass. However, I am not so sure about the radio reception because I don't see anything recognizable on SDR++. I think I might have killed my MMDS down converter unit. I pulled out my little nano VNA to just verify if my helix is working at all. The SWR is a little choppy, but it does seem to be working, so that shouldn't be the issue. I stuck the MMDS unit on the big dish here and on this little loop feed because I've used the loop feed before, I've used this dish before with S-band, and then some folks on Derek SGC's Discord suggested other satellites to look at, and it looks like I've screwed up the MMDS. It's not getting a signal. So I've tried resoldering this, and I think I've just made it worse, and it still doesn't work. So yeah, I definitely should have left the VHF connector on here and not messed with this end mount, even though the radio experts said, oh, I have to have an end mount. Yeah, it was working fine with the VHF. I should have just left it alone. Since I'm pretty sure I killed my MMDS, I'm just using a wideband RTL SDR LNA here. These are fairly cheap online. They're just not very good for filtering, so it'll probably get noise from 4G and FM and whatnot. I'm trying to parse the return that the dish gives me into machine-readable code so that my program knows where the dish is pointing, but unfortunately it gives me a lot of extra characters and sometimes the wrong variable types, so I'm still trying to deal with that. All right, we are running yet another test on another satellite pass. This is NOAA 19 going almost straight overhead, so we'll see again how does the dish handle passing through the 0-0 position. I've never actually gotten it to successfully do that, but we usually don't get that far before something else goes wrong. Now, the people who are constantly babbling on about ChatGPT in the comments will be overjoyed to know I asked ChatGPT for a couple solutions for two very specific problems with my code. Parsing the input from the dish, the regular expression, and calculating some math stuff for the relationship between how far the dish moves and how long it takes to move. Now, the math solution seems like it would work, but I can't actually implement that because the regular expression solution doesn't work, and ChatGPT's code does not successfully parse what the Trav'ler firmware is putting out. It's putting out numbers with a variable number of leading spaces. Now, I can't say that's obscure and proprietary because every time I call something proprietary, somebody gets in the comments and goes, oh, that was a standard at Microsoft from March to April of 1996, and you can't call it proprietary because it was an industry standard for 3 months. Either way, it's weird. I don't understand how to parse it. ChatGPT doesn't understand how to parse it, and that means we can't run our dynamic time calculation because we don't know what the current azimuth and elevation are. On the plus side, we are getting the signal from NOAA 19. So on the left side of the screen here, that is the S-band transmission. That means our dish is accurately tracking. It is locked on to NOAA 19, and we are receiving the data download. So we'll have to run that through SatDump later and see what it looks like. Now, unfortunately, it has derped out slightly. It did not gracefully handle the transition through 90 degrees. It spun all the way back around, and now it's confused about whether it should be going up or down. So I've changed my feed setup yet again. The current configuration is the S-band helical feed. We have a FM band stop because I was getting, again, a ton of FM broadcast radio interference. So we have that cut out with the band stop. We have the RTL SDR wideband LNA because I've killed the S-band one, but it seems to be working reasonably well for S-band with the addition of that band stop filter. Then that goes down to the Hacker F1. Again, because we killed the MMDS, we aren't down converting from S-band to L-band anymore, so we have to look directly at S-band. So the RTL SDR software-defined radio can't go above 1.7 gigahertz. We're looking at 2.2 gigahertz, and the Hacker F1 is the only thing I have at the moment that can look that high in the radio spectrum. All right, so here is what we downloaded from that pass, and as expected, there's a big continuity jump in the middle. There is basically a gap in the data because we lost tracking. So otherwise, these look very pretty. These are nice images. This is as good, if not better, than I've gotten from a NOAA satellite on S-band in the past, and they're just as good as what I got on L-band. It's the exact same data that you get on L-band, but S-band is a little more challenging to actually pick this up and track it and get it all working. So right here is where I have a problem. The dish looks like it's tracking, and it is tracking azimuth, but it is no longer tracking elevation, and that is because near the middle of the pass, the azimuth motor has to run slightly longer to get to each step, and it's basically not giving the elevation motor time to run before a new command comes in and kind of bumps that into an error condition. Some of the ChatGPT stuff came in that I don't understand it, and it's not working. So that's kind of why I don't like to use ChatGPT, because it gets things wrong, and it gets things wrong in a way that I don't understand, so I don't know how to fix its mistakes. All right, we did get some data that time, and again, we do have that discontinuity in the middle because we lost the elevation tracking towards the middle of the pass. and the signal wasn't as great. So we have a lot more static, a lot more noise, because this was a more distant pass. There were more trees and things in the way, so we got a little more interference from the radio signal, but we do have some recognizable imagery from NOAA 18. We have some cloud patterns. We can look at the thermal channels. All right, we're trying another pass. It is about 15 degrees Fahrenheit out here, and the Trav'ler is not happy about that. The other brand that I've used, the tailgater antennas, those tend to work a little better for cold, and those are actually preferred for ice fishing and cold weather use. These Winegard units, I guess you're just supposed to slap them on your RV and drive down to Nevada. You're not supposed to go ice fishing with these. You're not supposed to have your RV out in the winter, so they don't like it when it's cold, and this thing is refusing to start up right now. I hate to say everything is working perfectly, because usually as soon as I say that it stops working, but we do have a lot more progress on the S-band tracking antenna here. We have been successfully tracking satellites. We have been successfully receiving the signals. I do still have a couple issues, such as the meridian flip. When we go past 90 degrees or 0 degrees 360, it does want to spin itself around, and that doesn't always work. But for most satellite passes, it's been working pretty well. People often ask if they can do anything interesting with a small rooftop TV dish like this, and I often say that you really want a big C-band dish like the one up there, because it's much bigger, it picks up a better signal. But yeah, the standard sized rooftop modern KU band TV dish works perfectly well for an application like this. The tracker definitely helps. You can still do this manually tracking. I could be holding this dish in the air, aiming it at the satellite myself, but I'm not a very good tracker, so I wiggle around too much, and I really find that the motorized mount helps a lot. But if you have steadier hands than I do, and if you don't have a tracker, yeah, you could use a dish just like this with the 3D printed helical antenna feed, and you could get S-band satellites, or you could print a slightly different feed and get L-band satellites. So a small dish like this, still perfectly useful. Alright, so once again we have our setup here. I have the Python code controlling the dish. I have gpredict telling the Python code where to point that dish for the upcoming satellite pass. And then we have SDR++ over here reading the HackRF1, the software-defined radio. Alright, I'm pretty sure that is the encrypted DMSP signal. So, alright, there's the switch. That signal we're getting now is the unencrypted one from DMSP. So everything below that is encrypted. Now, I notice my dish is lagging a little bit, and that might be in combination with some of my code and just because it's cold and the motors don't want to run, so things have slowed down a little bit, and we might lose some data from this pass. This DMSP satellite is a fairly faint signal compared to some of the NOAA satellites and the other ones I've looked at, and it needs a pretty precise lock from the antenna. So if this antenna drifts off by a degree or even half a degree, the signal significantly decreases. And this is why I'm developing the motorized dish, because this thing is even worse doing it by hand. So I'm hoping I can fine-tune our motor mount system here a little bit better, and we can get difficult satellites like DMSP more reliably in the future. Alright, here's what we got from DMSP F18, and that is frankly terrible. Alright, so this is working pretty well as a proof of concept, but I have enough tweaks and changes and updates and improvements on the to-do list that I think I'm going to have to do a second video on this. For one thing, the tracking is still a little bit too slow to keep up with certain satellites. Not so much the speed of the satellite, but the signal strength, especially for like DMSP satellites. The signal strength is so low that you need to track it really carefully. With something like NOAA, I can get away with having a 1 degree move every second or so, but with DMSP it has to be right on there or we lose the signal. And DMSP is one that I really want to play around with on this, so that might have to end up being a second video. I would also like to change the routing of the wiring, get it through the internal wrapping, rather than having my feed line just hanging off the front. I'd like it to go through the dish, and then we can put the dish up on the roof and just basically leave it there, have it plugged in down in the house, run the thing from the computer in the house or in the garage. I don't have to stand out here in the cold with cold hands. And then there are a couple other tweaks and changes in the code that I can do. So I think we're gonna wrap this video up because we are at a point where we are consistently getting S-band signals. We are consistently able to track satellites with the dish system. and that's a good place to stop. We're getting some pictures, we've got some good data off of the NOAA satellites. I think I'm gonna wrap it up here, and we're gonna do some of those other changes in a follow-up video, because this one is probably already running too long. Once again, I'd like to thank Derek SGC for designing these helical antennas for 3D printing. I'd like to thank PCBWay for sponsoring this video and offering all kinds of interesting PCB creation, 3D printing, and other creator services. And finally, thank you to everyone out there for watching, and we'll see you next time.